Good morning, everyone. Welcome to Chemistry with Professor John. All right, let's do this. IR, mass spec, and NMR. Okay, that's going to be our topics for today. We might not be able to get all three of topics in one video, but we'll do our best. All right. Now, I'm going to go through the theory really quickly, get straight to the spectra. So how to understand the signal and what's the focus, what do we get out of it. Okay, all right, let's start with IR stands for infrared spectroscopy. And if you look at IR, the electromagnetic radiation spectrum, IR wavelength is from about 2500 nanometers to 16,000 nanometers. So that's not a lot of energy, compared to X-ray or gamma, right? So if you take that and convert that to centimeter, and then inverse that 1 over lambda, the wavelength, you get around 4,000 inverse centimeters to around 600 inverse centimeters. All right, now the larger the frequency, this is called the frequency, not the actual frequency, but proportional to the frequency, called a wave number, by the way. The larger this wave number, the more energy. So you can see right here, more energy, lower energy, right? Okay, so when you have a sample, when you have your compound, you put in either it's 100% or with solutions. Usually we do 100%. We put on the plate, and then you put it on the IR machine, and then the IR machine will hit it with IR with certain intensity, and then the sample will absorb some and then release the rest. So now if you have 100% transmittance, that's not good. I mean, the sample does not absorb anything. That's why you don't see any signal. If the sample absorbs some or a lot, then it's close to zero transmittance. Okay, so you start seeing signal, right? Okay, those are meaningful signal due to special bond. That's functional group. Okay, so that's IR excited the bond, like a C double bond O or a C double bond C, or even CH bond. That's not anything special, but it's a bond. And making the bond vibrate by stretching or waving, all kinds of modes of vibrations. That's how the detector detect and when they relax, the detector will detect the that energy. Okay, so and here are what being observed. A CH bond around 3000, CD bond, that's deuterium, and then CC bond 1200. Okay, now you got here's a good comparison between among the CC double bond, CC single bond, double bond, or triple bond, and you can see there's a good trend of increasing energy as you got more bonds, right? Same for CN versus CN double bond, CN triple bond. So it's really hard to tell between the CC bond or the CN bond, okay? Because they all show up pretty much the same area, the signal. CO single bond versus CO double bond. Um, so the trend as well. And I don't think we'd run into CO triple bond. Okay, so those are functional group or active, special bonds. Now, in order to IR to read those, it has to be not symmetrical. So these molecules right here, inactive, so you don't see. You put it in an IR machine, you don't see any signal because they're pretty much symmetrical, very symmetrical. Okay, it's got to be really unsymmetrical to see the vibrations. Okay. Now, double bond about 1600, and double bond about 1600. Some conjugations does decrease the energy a little bit. Conjugation means you got a double bond, single bond, double bond, single bond, double bond. Okay, or just like this case, the benzene ring. A CH bond, regular CH bond in alkane 2900, 3000. Double bond, they're really close. Triple bond, a little stand out there. It's still a CH bond though. It's just on the carbon that's sp. This is sp, this is sp2 carbon, and this is sp3 carbon. Okay, so that's the difference. Okay, and we got alcohol, very broad signal like that, around 3,300 plus minus. That's because of the hydrogen bonding. Carboxylic acid the same way for the OH. Now, for amine, like primary amine, this is NH2, secondary amine is NH. So you're going to see 2 spike, and then you're going to see 1 spike because there's only 1 hydrogen. Okay. Pretty much that's it. It helps us to identify the special signal for functional group. So when you run the IR, you pretty much can tell your compound is a ketone, aldehyde, or carboxylic acid. They're all the same brand, or even ester, right? Or alkene. If you have an alkene, then if you really have good experience, you have a ketone and a double bond alkene, then it dropped down to just below 1700, right? Okay, you got more here. All right, so IR is good. Now, real quick on the mass spec. Now, IR is good. It tells us the functional group, but functional group alone is not good enough for us to figure out what the structure is. The mass spec is the next one that's helpful. Okay, mass spec, it help in a way to figure out. The first thing is the molar mass, and then with all the fragments, if we're good, we can figure out the structure as well. Okay, so if you take a molecule, which is M, right? That's a neutral molecules, and you hit it with high-speed electron, and that's I believe we use rhenium. That's the elements, the rare earth elements that generate electrons in the mass spectrometry machine. We hit the molecules with high-speed electron. So, in a molecule, there's a lot of bonds. So when a molecule get hit, and then that electron steal 1 electron from the molecules M, so the molecules M become a radical. It's a broken bond, and because it loses 1 electron, so it become positive, and the single electron become a pair of electron. We're happy. Okay, so that's molecular ion. It's not stable. It's gonna break down into pieces, and we call that process is fragmentations. And if we identify those small branches, uh, we can, with the hope that we can put together the molecules. Okay. Now we also see a signal for M plus, and that's the molecular um, molar mass, right? Or the molecular mass of M plus. And usually it's very small signal, right? Okay, and for the machine to work, we have to do the ratio, the mass over charge ratio. If the charge is +1, then the mass, divided by 1 is the same anyway. Okay, so that's M plus, and then you see all the fragments. Okay, the most stable is the base peak. That's the one with the highest abundance. Okay. Now with the molar mass, we that will help us to figure out the structure and all the fragments. The big M plus break down into smaller pieces, and then the machine will identify those by the mass. The charge is 1, so divided by 1, so it's the same. Okay. So if you run into a mass of 29, then it's probably a CH2 CH3, right? CH2 CH3. Yeah. If you run into the mass of 15, you're probably dealing with a methyl cation, right? Which is rare. But anyway, here we go. Here's a good one. If you do the calculation, it should be 77. M over Z is 77. And no, I'm sorry, plus 12, 14, that should be 91. 77 is just the benzene ring, okay? So it should be a 91. If you see a 91, it's got to be a toluene plus, right? Things like that. Here's another one, Okay, so the mass spec is very helpful in that way. When you see elements with isotope, then sometimes you see more or less due to the isotope. So bromine, for example, you got a 2 isotope, 79 and 81. So, and they're different in 2, so that's why you see M plus 2. Okay, M is 79 and plus 2, that would be 81. And you also see M plus 1. Okay, so you're going to see 2 signals instead of 1. You can see M plus, and then you see M plus 2. And we talk about M, radical. Okay, that's E. So when you see that, and they are on the same height, then you know you got bromine. If you see two signal like that, equal signal, and say what's going on, M plus, and then you see M plus 2, that's because of the bromine. It's not because of carbon or hydrogens. Okay, that's good enough for mass spec for now, and then let's go on to NMR. NMR is the most sophisticated method among the 3 spectroscopic method, among the 3 methods, IR, mass spec, and NMR. Now this one actually, you'll be surprised, we're using very simple, very low energy, radio frequency energy, and we're going to use that energy to hit the nuclei, in the presence of magnetic field. And that's the goal, each nucleus, for example, like a hydrogen nucleus, or a carbon-13 nucleus. So each nucleus is like a magnet, all right? And under magnetic field, it's gonna spin. It has its own normal spin, but under induced, or the magnetic field that we create is we can control that. Okay, so let's say hydrogen or carbon nucleus. It's got two different spin, the low energy one and the high energy one. So let's think about the alpha uh, spin state and beta spin state. So let's say alpha is low energy and alpha is a high energy. Now the when the alpha when the nucleus is in the alpha spin state, absorb just enough energy, it will switch to the beta spin state. That's a simple way to look at it, right? Just like we're at the normal state, but if we drink a cup of coffee and we got extra energy from sugar and caffeine, we got excited. So we got to the next stage, awake, right? That's higher energy. Same for molecules here. They don't need coffee; they need just delta E, right? And that's actually low energy. That's good to get to the beta spin state, and that's how we get them more excited. And when they fall back uh, to their normal alpha spin stage, the detector will detect that. Okay. Now, different type of hydrogens will absorb different energy. Okay, so you got different group of hydrogens. You got a CH2, CH3, CH2, and here you have three different kinds of hydrogens. Okay, you got CH3. Those three hydrogens are the same, and that's the first group. And then you got CH2. That's the group second one, and then you got the hydrogen by itself that form its own group. They all in different electron environment. Okay, electron cloud environment. The first one is very close to oxygen, and the second one be closer than the three hydrogen in group C. So it turns out it's going to show up, different signal, right, for all this guy. And yeah, you got three different signal, okay, and that's the first thing we're going to be looking at is the chemical ship. Is the ratio between the absorbing frequency and the frequency of the applied magnetic field, which is the machine. Okay, so chemical ship is the energy, which is the frequency of the energy absorbed by the group of hydrogens versus the total frequency of the machine, the spectrometers. Okay, with TMS, trimethyl, tetramethyl silicon, or tetramethyl silane as a reference, okay, everything else is going to be based on that. Now we got a CH3, that's the first group, and then we got the hydrogen of the OH, really high. Okay, now here I would like to talk about shielding and de-shielding effect. Okay, when a closer hydrogen to the high electronegative atom, such as oxygen, fluorine, chlorine, higher chemical ship. They also called low field, lower field, more higher de-shielding of hydrogen nucleus. De-shielding. Okay, de-shielding by electron clouds. Okay, so in other words, to make it simple, hydrogens next to oxygen will be very positive. Almost no electron, really exposed. No protection from electron cloud, really exposed. So that's going to be ready to absorb that delta E. Lower field, which is higher energy, and that's why it show up, pretty high chemical ship, versus this, a little bit less because it's one step away from the oxygens. Okay, and then if you have CH3, that's whole group right there. There's no oxygen at all, no electronegative atoms at all, so it's really low. It's 0.9, and then inside here, you got two hydrogen. That's about 1.3, and then outside is the same, 0.9. Okay. Okay, so that's how we recognize them, right? By chemical ship. Okay, you guys see really low. If you got one chlorine, that's 3.0. If you got two, that's almost double. If you got three, that's higher chemical ship, because really highly de-shield, highly de-shielded by electron, because the 3 chlorine take all electron cloud away toward themselves, right? Okay, you got double bond. It supplies, it's pretty high, but you got a CH3, that's a step away, so that's lower. You got the hydrogen right on 3 double bond, very high, so on and so forth. You got hydrogen, these are extremely high. Okay. All right. So let me skip over this one. So that's chemical ship, right? Very important. Okay, right here, a couple practice for us. We got 9 hydrogens, right? 9 hydrogens. That's lower than this one, because this one is right on, right on the oxygens, right? Almost on the carbon next to oxygen. So it's pretty high. It's like 3.2. Okay, versus 1.2. All right. Now what's the ratio here? I mean, this looks like a 9 hydrogen versus a 3 hydrogens. So you take 3 hydrogen versus 9 hydrogens, you do the ratio, it's going to be 1 versus 3. Okay, lowest ratio. So we got 2 signal. Those are 2 different groups of hydrogens. They cannot be in the same signal, right? They have to be 2 different signal. The first one on your left is a higher chemical ship because it's more de-shielded, close, right on the oxygen. The second one's a little bit further away, so lower chemical ship. Here's another one for you, that's to point out for you. You got 9 hydrogens, beautiful, right? And then 3, and then 2 hydrogens right there. And here, obviously you got 3 here, 3 here, and 3 here. That's the same group. That's gonna be 9, so that's gonna go to the highest one. You can also tell by the intensity. And you got 1 little hydrogen, so obviously it's gonna be right there. And you got 6 hydrogen, it's gonna be right there. So the ratio will be 1 to 6 to 9. That looks right, right? Okay, and there's one here for you. All these 5 hydrogens, they're really high. You look at the table, it's like 7 to 8. Now if you got 3 hydrogens next to oxygen, so that's probably that. And then you got 2 hydrogens this guy right here. And higher chemical shift because there's a benzene on the left, there's oxygen on the right. And so on and so forth. 6 hydrogens. And then this one is right here. And then you got the aldehyde is extremely high, like 9 to 10. That's because it's next to double bond O. That's why. This one, 2-bromine, you got 2 hydrogens. You got this, right? You got that. You got that. We got 4 different signals here. Okay, now which one is which? The one on the oxygen, we probably go for that one. And then you got 2 hydrogen here, probably that one. And then 6 hydrogen, you can tell by the height of the signal. And now it's got a little tiny signal right here. It's tiny, but it's actually wide. So the area under the curve is pretty good, you know. Okay, now the next one, let me talk about this real quick and then we'll come back to this. Now, this one is called splitting, okay? The splitting meaning the type of signal, okay? Now it's a little more complicated. We got A, B, C. I labeled them A, B, and C. Okay, so A, you have 2 different hydrogens. I mean 2 hydrogens, but they're gonna be on the same signal because they are equivalent. B, you got 3 hydrogens on the same signal. They're equivalent. And then C, you also get 3 hydrogens. So we got 3 different signals, but they're not all single peaks. They are different shapes. HA is going to show up as what we call a 4-spike quartet. 4-spike. A 4-spike signal or peak. Okay. Now that's known as a quartet. This is a triplet. That's a 3-spike signal or peaks. Okay, Y, okay, and then you got HC. It's just a single one. It's called singlet. S, triplet is T, quartet is Q. Okay, now let me explain real quick. The first one, okay, and this is depends on n plus 1. Okay, so the rule is n plus 1 rule. N is the total hydrogens on neighbor carbon. All neighbor carbon. On the left, on the right. Okay, so for A, the 2A hydrogens, look over to the right, and there's a carbon with 3, there's a neighbor carbon with 3 hydrogens. So that's why it's a 3 plus 1. And that's why you got 4 spike. Okay. Now, the B, okay, there's 3 of them. And the B, look over the left side, and there's 2A, so 2 neighbor. That's why it's 2 plus 1 equal to 3. That's why you got 3 spike. And then you get to this one, C, there's no neighbor. Just one, you know, little signal. That's a singlet. So it depends on the neighbor carbon. Okay. Remember, this is not the intensity. This is not how tall the peak is or how wide the peak is. This is the intensity. And this is the multiplicity. The next door, okay, carbon. All right, it's a little bit more sophisticated than the intensity of the signal. The intensity of the signal is just simply how many hydrogens, okay? All right, so and this is, you know, more theory about how you identify what kind of signal. Is it a singlet, doublet, triplet, quartet, or quintet, or multiplet, so on and so forth. Okay, so that should be good for you to recognize all the signal, which one belong to which group of hydrogens and which signal belong to which, functional group, things like that. Okay. I'll see you guys in the next video for more details about uh, this stuff, really fun stuff, NMR. Thank you, guys.